In the final months of 2017, an extraordinary visitor entered our solar system. It moved with astonishing velocity, cutting silently across the darkness before slipping away once more into the cosmic unknown. Scientists named it Oumuamua, a word from Hawaiian meaning a messenger from afar arriving first. It was the first object ever observed to originate from beyond our solar system. Yet its origin alone is not what has puzzled astronomers the most. What truly set Oumuamua apart was not where it came from, but what it did. As it passed through our part of the galaxy, it displayed behavior so unusual and so resistant to the laws of known physics that some researchers found themselves drawn to a bold and controversial conclusion. They began to wonder whether this object might not be natural at all, but instead a piece of alien technology. What is Oumuamua? What precisely did it do? And perhaps most intriguingly, are there others like it? Drifting silently through the void. Today we delve into the mystery of this elusive traveler. We will explore the many theories that attempt to explain its strange journey and examine the bold proposals that aim to pursue it across interstellar space in search of answers. Among scientists, there are differing views on how many such interstellar objects may be passing through our solar system at any given time. Some estimates suggest that thousands of these visitors could be entering our region of space each day, crossing the orbit of Neptune unnoticed. At first glance, this may seem implausible. But to understand why this number is taken seriously, we must first consider the true scale of our solar system. It extends far beyond the familiar orbits of the planets. Beyond Neptune lies the Kuiper Belt, a frozen realm of icy bodies. And beyond even that is the Oort cloud, a vast spherical shell of ancient debris that may contain trillions of comets, each loosely bound to our sun's distant gravity. Many of the comets we observe near the Sun likely originated from this outer frontier. Their paths are vast ellipses that take tens or even hundreds of thousands of years to complete a single orbit. These long journeys are often triggered by a gravitational nudge. A passing star or another massive body can disturb the delicate balance of forces, sending a distant comet plunging inward toward the heart of the solar system. In a cosmos governed by gravity and time, these distant objects hold stories that began long before the birth of human civilization and may continue long after we are gone. We often imagine our solar system as a tranquil, fixed collection of planets and stars. But in truth, it is anything but still. The entire system is in motion, sweeping through the Milky Way in a vast orbit that takes hundreds of millions of years to complete. As we journey along this immense path, we encounter the gravitational fields of countless other stars. Even those several light years away can exert a subtle yet powerful influence. Sometimes, that influence is enough to draw a distant comet inward, sending it hurtling toward the Sun in a fiery arc. At other times, the effect is quite the opposite. A comet may be nudged outward with such force that it escapes the Sun's grasp entirely, cast adrift into the galaxy as yet another interstellar wanderer. These liberated objects join a vast population of similar bodies, thought to be moving between the stars, hundreds of trillions of them. Drifting through the galactic deep, our Oort cloud, the icy halo at the outermost edge of the solar system, is not a unique feature. It is believed that many other star systems harbor similar reservoirs of ancient material. This means comets are not only born and lost within solar systems like ours, they are also exchanged, captured, and released across the galaxy in an endless celestial ballet. Even so, the comets we have observed in our own Oort cloud tend to share a common fingerprint. Their compositions are remarkably alike, which suggests that the majority were formed alongside our Sun and have remained with it for billions of years. But as our solar system continues to voyage through the galaxy, it inevitably crosses paths with other travelers. Many of these interstellar visitors have long since been separated from their native stars. They often arrive from the direction of the constellation Vega, the very region toward which our solar system is currently headed. Though the Sun does occasionally capture such objects, most arrive with such tremendous speed that they cannot be held. They sweep through our solar system in brief, silent encounters, their trajectories altered slightly by the pull of the Sun before vanishing once more into the void. Oumuamua was one of these rare interstellar guests. It was first detected on the 19th of October in the year 2017 by astronomers at the Halakala Observatory in Hawaii. What they saw would spark both excitement and debate, as the object's behavior soon proved to be unlike anything they had expected. When Oumuamua was first detected, astronomers initially believed they were witnessing a comet. It was given the designation C-2017U1. But closer scrutiny revealed something unusual. There was no visible coma, no glowing cloud of gas typically surrounding a comet as it nears the Sun. Without this defining feature, it could not be classified as a comet, and so it was redefined as an asteroid, receiving the designation a 2017U1. This reclassification marked the first time an object had its category changed in such a way after discovery. As astronomers mapped its orbit with increasing precision, a more startling realization emerged. This object was traveling far too quickly to be gravitationally bound to the Sun. Its path through the solar system did not curve into an ellipse. Instead, it followed a hyperbolic trajectory, an open path that indicated it had come from beyond and would never return. It was clear that this object was a visitor from interstellar space. In honor of its extraordinary origin, it was given the name Oumuamua, a Hawaiian word meaning scout or messenger from the distant past. The International Astronomical Union, recognizing the uniqueness of the discovery, created an entirely new classification. The letter I for interstellar was introduced, and the object became known as 1I-2017U1. The scientific community was filled with excitement. For the first time, researchers had the opportunity to study an object born of another star system. What might it reveal about the cosmos beyond our Sun? Could it resemble the celestial bodies we know, or would it carry alien characteristics, shaped by an entirely different stellar nursery? As observations continued, something unexpected began to emerge. Oumuamua's physical nature was puzzling. It was small, estimates ranged from 100 to 1,000 meters in length. Its brightness changed dramatically over time, suggesting it had an elongated shape, perhaps something akin to a cigar or possibly a flattened disc. This variation in brightness appeared to be tied to a rotation of roughly 7 hours, as it tumbled end over end through space. Unlike most objects that spin along a fixed axis, Oumuamua was tumbling chaotically, as if unsettled by some ancient cosmic event. Its shape was not the only mystery. If it resembled an asteroid, it would have most likely originated from the inner regions of its home system. That led to more questions. How could such an object be ejected with such speed and precision? Could it have been the result of a massive collision, some ancient cataclysm beyond our reach? Or perhaps it truly was a comet after all, one that had wandered through the cold vacuum of interstellar space for countless ages, accumulating a layer of dust that concealed its icy heart, preventing the Sun from igniting the familiar cometary glow. While these were fascinating questions, there was one mystery that overshadowed them all. It was Oumuamua's movement. The object reached its closest approach to the Sun on the 9th of September in the year 2017, moving at a breathtaking speed of 87 kilometers per second. But as it left the Sun behind, something strange occurred. Rather than slowing down as expected, it accelerated. An unexplained increase in velocity seemed to push it further into space, against the gravitational pull of the Sun. Rob Warwick, The astronomer credited with its discovery noted that Oumuamua's motion could not be explained by the familiar mechanics of asteroids or comets. It was not behaving as it should have, not by the standards of physics. Although the acceleration was modest, only about 17 meters per second at its peak, it was enough to challenge established understanding. For the brief time that scientists were able to observe it, they confirmed that Oumuamua was straying from its predicted path. In the realm of physics, an object cannot accelerate without a force to drive it. This left scientists searching for an answer. What could possibly be pushing Oumuamua? Some proposed solar radiation pressure, a subtle force produced by the stream of particles emitted from the sun. While this phenomenon can indeed nudge small objects in space, calculations showed it was far too weak to account for the motion observed. Assuming Oumuamua was an ordinary asteroid, attention turned to comets. In our solar system, comets frequently accelerate as they near the sun. Their icy surfaces warm, turning to gas that vents into space, forming the iconic tail. This process acts like a natural thruster, propelling the comet away from the sun with gentle but measurable force. Could this be what was happening with Oumuamua? When scientists turned their instruments toward Oumuamua, they expected to detect the usual signs of a comet dust, gas, and perhaps a shimmering tail. But nothing came. The Spitzer Space Telescope, renowned for its ability to detect faint heat signatures in the infrared spectrum, devoted 30 hours to observing the object. It saw nothing. Oumuamua emitted no detectable warmth, no glow, no tail. This absence was deeply unusual. Typical comets possess bright, expansive comas that Spitzer can easily identify. Yet Oumuamua remained silent and cold. Even more puzzling, the telescope's readings suggested that the object was at least 10 times more reflective than an average comet. Such brightness hinted at a surface potentially metallic in nature, unlike the dusty ice of traditional comets. This deepened the mystery. What exactly was Oumuamua? To explore the possibilities, two competing theories began to emerge, each supported by a different scientist, each painting a radically different picture. The first came from Harvard astrophysicist Avi Loeb, who proposed that Oumuamua might be something entirely unprecedented, alien technology. In a provocative argument published in 2018, Loeb suggested that the mysterious acceleration observed could be explained by the pressure of solar radiation. But this, he said, would only be possible if Oumuamua were far thinner than previously assumed. He estimated it might be no more than a fraction of a millimeter in thickness. Such a structure, possibly 1,000 meters long and barely a millimeter thick, would be extraordinarily unlikely to occur in nature. Loeb concluded that Oumuamua could be artificial, a light sail designed to harness the energy of starlight, perhaps to travel between solar systems. His theory drew immediate attention, but also significant criticism. One of the most prominent counterarguments came from Darryl Seligman, a postdoctoral researcher at Cornell University. In 2020, Seligman co-authored a paper proposing that Oumuamua was composed largely of hydrogen ice, and that the observed acceleration was due to invisible hydrogen gas escaping as the object warmed near the sun. Such a substance would have gone undetected by the instruments observing it, including Spitzer. Loeb challenged this idea. In a follow-up study, he demonstrated that hydrogen icebergs could not survive the journey. The radiation found in interstellar space, he showed, would have evaporated such fragile structures long before they could ever reach us. He remained firmly convinced that the most plausible explanation was an artificial one. Seligman, however, was undeterred. He abandoned the notion of a pure hydrogen iceberg, but continued to explore the possibility that hydrogen gas was still involved in Oumuamua's propulsion. Yet he had no mechanism to explain where the hydrogen might have come from until he met Jennifer Bergner. an assistant professor at the University of California. Bergner introduced a compelling laboratory phenomenon. Under extreme cold and intense radiation, water ice can trap hydrogen gas within its molecular structure. Later, when warmed, this hydrogen is released as the ice rearranges itself. Given the abundance of water ice and radiation in space, such a process seemed plausible. Together, Seligman and Bergner proposed a new category of object, the dark comet. Unlike traditional comets, these bodies would not emit dust or display bright tails. Instead, they would undergo subtle chemical changes that quietly released pockets of invisible gas, providing just enough thrust to alter their trajectories. Though Loeb remained unconvinced, publishing 2 more papers refuting their claims and accusing them of flawed mathematics, Seligman was already looking ahead. If Oumuamua truly represented a dark comet, might others exist in our solar system? He and his colleagues began reviewing the data. They searched for objects that were not interstellar, but that nevertheless exhibited unexplained acceleration. Remarkably, they found 6. These were all small bodies, some no larger than 3 meters across. They appeared to be ordinary asteroids, yet none had visible tails or emitted gas, and all showed subtle accelerations that could not be explained by gravity or solar radiation alone. Each of these 6 objects was a near-Earth object, located close enough to make future exploration feasible. And one of them, in particular, was already scheduled to be visited. This object, named 1998 KY26, is set to be approached in 2031 by the Japanese spacecraft Hayabusa 2. Originally launched in 2014, the mission successfully completed its primary goal of retrieving material from an asteroid and has since been extended to study additional targets. Among them is this fast-spinning body, which rotates once every 10 minutes and is believed to be rich in water. Once Hayabusa 2 reaches it, we may finally gain insight into the mysterious force driving its motion. We may learn whether dark comets truly exist or whether something else is at play. As for Oumuamua, the scientific debate continues. No one can say with certainty which explanation is correct, but the discovery of other accelerating objects within our solar system suggests that Oumuamua may not be unique. It may be the first of many. If further studies confirm that these objects accelerate due to invisible outgassing of hydrogen, then Seligman's theory will be vindicated. But if, against all expectations, one of these bodies reveals itself to be artificial, then Avi Loeb's controversial claim may find dramatic support. One might consider the latter possibility far less likely. After all, objects like 1998 KY26 have been imaged in exquisite detail, and they do not resemble alien technology. Yet the truth, whatever it may be, promises to deepen our understanding of these enigmatic visitors. Studying dark comets within our own solar system may illuminate the nature of Oumuamua. But what of other interstellar objects? Have we seen more? Indeed, we have. The second confirmed interstellar visitor was discovered not long after Oumuamua. It was given the designation Tuai Borisov. Unlike its mysterious predecessor, Borisov appeared much more familiar. It had a large, luminous coma and a vast tail stretching thousands of kilometers across nearly the size of 14 Earths. Though its closest approach to the Sun, in 2019, placed it beyond the orbit of Mars, and thus beyond the reach of the naked eye, its structure resembled that of a textbook comet, roughly the same size as Oumuamua. Borisov confirmed that other stars do send forth icy messengers, crossing the void of interstellar space to briefly visit our Sun. But Borisov's tale is simpler, more conventional. Oumuamua remains the outlier. It is still the enigma. After its closest approach to the Sun, the interstellar traveler began to disintegrate. For a comet of its size and proximity, this was not unexpected. Its composition, while somewhat uncommon, fell well within the bounds of what is typically observed. And because it never came as close to the Sun as Oumuamua did, its path was only mildly perturbed by the Sun's gravitational pull. In the end, aside from its interstellar classification, this object was relatively ordinary. But others like it, some officially interstellar, others not, offer further intrigue. One such object is designated C280E1. It was once thought to belong to the solar system, with a vast orbital period of over 7 million years. At its most distant point, it ventured an astonishing 1.17 light-years away from the Sun. Yet during a close encounter with Jupiter in 1980, everything changed. Jupiter's massive gravitational field gave the object just enough energy to push it beyond a closed orbit. Its path became hyperbolic, and in time, it will leave the solar system forever, joining the ranks of the interstellar wanderers. Interestingly, the reverse has also occurred. Interstellar objects have occasionally had their speeds reduced enough by Jupiter's gravity to become permanent residents of our solar system. Jupiter alone appears to have the mass necessary to capture such objects. Other planets simply lack the gravitational strength to act as a third body in these intricate dances of motion. Two such objects, Matchholes 1 and Hyakutake C1996b2, are thought to be captured interstellar comets. Their unusually elongated orbits and highly distinctive chemical compositions suggest origins far from our Sun. These characteristics make them fascinating targets for future study, as the solar system may have already done the hard work of collecting interstellar material and placing it within reach. Another telltale sign of extrasolar origin lies in the direction of an object's orbit. Most bodies in our solar system follow the same general direction around the Sun. But if an object travels in the opposite direction, it may have come from beyond. One such object is 514107 Kipaukoela. Unlike most interstellar bodies, this one is an asteroid, not a comet. If it was once a comet, then its volatile materials may have long since been burned away, implying an ancient capture early in the solar system's history. Its orbit is particularly fascinating, locked in a 1-to-1 resonance with Jupiter. That means it follows a path that keeps pace with the giant planet, suggesting a long-standing gravitational relationship. Yet despite all these discoveries, the true nature of Oumuamua remains unresolved. One of the most pressing mysteries is its origin. We know it came from far beyond the boundaries of our solar system, but exactly where remains unknown. Astronomers have traced its journey backward through space and time, pointing roughly to the direction of Vega in the constellation Lyra. Some models identified 4 possible stars from which Oumuamua could have originated. One of them lies over 80 light-years away. But none of the candidates have provided a definitive answer. Today, Oumuamua is more than 6 billion kilometers from Earth, still moving steadily outward at 26 kilometers per second. It now heads toward the constellation Pegasus, its distance comparable to that of Voyager 1 when it captured the famous pale blue dot. Even if Oumuamua is not a product of alien engineering, its status as the first confirmed interstellar object to visit our solar system has made it an object of enduring fascination. Unfortunately, it was not noticed until 40 days after its closest pass to the Sun, by which time it was already 33 million kilometers from Earth. Ground and space telescopes were hurriedly directed toward it. Yet only weeks later, by the middle of December, the object had grown too dim and too distant to study, even with the most powerful instruments available. The data we collected was limited, and the questions it raised were many. For some scientists, the only path forward now is to catch up with it. But doing so is no small task. There are 3 formidable challenges. First, Any spacecraft would need to reach extraordinary speeds to overtake it. Oumuamua is already 6 billion kilometers away, traveling at more than 26 kilometers per second. No existing chemical rocket can match that velocity. Second, once a craft does reach Oumuamua, it must decelerate in order to perform meaningful study. Without slowing down, it would simply flash past the object in a brief encounter, offering little opportunity for detailed observation. And third, the target itself is incredibly small, no more than 1,000 meters long, lost in the vastness of space and tumbling as it travels. Yet despite these daunting obstacles, research groups have begun drafting plans to intercept it. The most promising proposals make use of gravity assists, using the mass of other planets to sling a probe outward at ever-increasing speeds. One of the best-known ideas comes from Project Lyra, an initiative developed by the Initiative for Interstellar Studies. They have proposed two viable flight paths for a mission to pursue Oumuamua. The first involves a complex series of maneuvers. The probe would first escape Earth's gravity, heading toward Jupiter. From there, it would fall inward toward the Sun. Because Jupiter orbits more slowly than Earth, this maneuver requires less energy. As the probe nears the Sun, it would reach maximum velocity. At that precise moment, its engines would fire, executing what is known as a solar orbit maneuver, an energy-efficient technique that uses the Sun's gravity to boost a spacecraft's speed dramatically. With this method, the probe could achieve an exit velocity exceeding 70 kilometers per second, more than enough to catch Oumuamua. But there are limitations. A flyby that close to the Sun demands an advanced heat shield to protect the craft. The Parker Solar Probe has proven such shields are possible, but they add significant weight, nearly 73 kilograms, which limits the payload. The trajectory is also long and complex, requiring the probe to circle between Earth, Jupiter, and the Sun before finally heading toward its target. And most importantly, the mission would involve techniques never before attempted, reducing its readiness and increasing its risk. There is, however, an alternative. The second proposed path from Project Lyra begins with a launch from Earth, followed by gravity assists from Venus and Earth, then a deep space maneuver to reorient the probe. After another Earth flyby, the craft would use Jupiter's gravity to launch itself outward. This route is shorter and does not require a heat shield. Though it would yield a slower final velocity, this reduced speed would make it easier to decelerate during the approach, allowing for more precise study. Project Lyra has outlined at least two potential launch windows between 2030 and 2033, with an expected rendezvous by the year 2048. One of the project's lead designers, Marshall Eubanks, believes such a mission is not only feasible, but inevitable. As interstellar exploration becomes more common, Oumuamua will remain a closer and more accessible target than planets in other solar systems, even a century from now. Still, one wonders if we might have done better. What if we had spotted Oumuamua sooner, months before it arrived, rather than after it had already passed? Karen Meach, an astrobiologist at the University of Hawaii who led the early characterization of Oumuamua, believes we are close to achieving just that. Thanks to new technology and upcoming surveys, we may soon be able to detect similar interstellar interlopers long before they reach our solar system. A new chapter in our search for interstellar visitors is about to begin. The Rubin Observatory, expected to become operational in the final months of the year 2025, will bring with it unprecedented capabilities. It is predicted to detect objects like Oumuamua as much as 3 months earlier than the telescopes currently in use. This powerful instrument will also initiate the Legacy Survey of Space and Time, a monumental catalog comprising over 2 million images collected across a full decade. With such an archive, scientists will be able to track even the most subtle shifts in the night sky, including the movement of comets and asteroids with extraordinary precision. A study published in 2023 estimated that this survey could identify up to 70 Oumuamua-like objects each year. But even with this promising outlook, more proactive steps are being taken. The European Space Agency's Comet Interceptor mission, set to launch in 2029, represents a bold and innovative approach. Unlike traditional missions that are launched with a known destination, this probe will be sent into space to wait. It will remain dormant for up to 3 years, watching and waiting for a comet or interstellar object to pass close enough. When the moment comes, the probe will awaken, intercept the target, and perform a close-range flyby, capturing detailed data and creating a 3-dimensional map of the object. It is a remarkable mission, the first of its kind launched without a known target. Yet it carries an inherent risk. We do not know how long we will have to wait for another visitor like Oumuamua. If none pass within reach during that window, the mission may go unfulfilled. And even if it succeeds, it will tell us nothing new about Oumuamua itself. That object, now drifting far beyond the reach of our telescopes, may take its secrets with it into the cold silence of interstellar space. Waiting for the next visitor, while reasonable, may mean leaving Oumuamua behind forever. Given this uncertainty, perhaps launching a dedicated mission to pursue Oumuamua is not such a far-fetched idea after all. From a technical standpoint, it is entirely feasible. There is nothing about such a mission that lies beyond our current knowledge or engineering capabilities. But technical feasibility is only one part of the equation. There remains the question of cost. Space missions demand vast resources, time, funding, materials, and expertise. Perhaps the wiser path is to wait, to trust that another visitor will arrive, just as Oumuamua did. After all, if it happened once, it can happen again. In the end, we are faced with a fundamental question. What price are we willing to pay to satisfy our curiosity? At Project Lyra, the answer seems clear. For its researchers, the pursuit of Oumuamua is a risk worth taking. Is it worth it for the rest of us? So far, many theories have attempted to explain Oumuamua's bizarre behavior. Some say it was a dark comet. Others propose alien origin. Some suggest possibilities that lie between. But without more data, we are left in the dark. It may be that none of our current theories are correct. That, too, is the beauty of science. The more we explore, the more surprises we find. And with every new mystery, our understanding grows. Perhaps, in time, other objects will visit us from the stars, objects that will offer new clues, new insights, and greater clarity. Perhaps they will help us finally understand what Oumuamua truly was. Even now, as we scan the sky for invisible forces guiding unseen visitors, we are filled with a sense of wonder. The possibilities are endless. But here lies the paradox. Unless we take the leap, unless we choose to pursue the unknown, we may never uncover the truth. And that, in its own way, is both the tragedy and the magic of our cosmic quest.